Hello, everyone, and thank you all so much for joining us today for another XP Live webinar. My name is Catherine Tran, and I'm part of the marketing department here in the XP Solutions Portland office. So today's webinar will be a discussion of actual questions and projects that engineers have discussed with us over the past few months. These are questions that they couldn't solve anywhere else or were real head scratchers until we took a deeper look at how XPDRAINAGE can easily assess real-world stormwater systems in all their complexity. Today's presenter is Zach Sample, our Stormwater Products Manager. He has over 10 years of civil engineering experience in site design, stormwater planning, and hydraulic analysis. Zach has performed a number of advanced water resource studies, including hydrologic and water quality system assessments, as well as 1D and 2D hydraulic river and floodplain studies. During his time with XP, Zach has helped hundreds of clients with their models, so his voice may be familiar to some of you. Thank you all for joining us today, and welcome, Zach.
Hi, everybody. Thanks, Catherine. Thanks for joining today. Let's jump right into it. So the agenda for today, what I want to talk about is a brief introduction of kind of what this XPDRAINAGE thing is, the stormwater design tool that we offer, and then jump right into actual support questions, questions that came to me or other technical staff here that we had to kind of help the engineering community figure out. So we'll briefly look at these problems and then jump into how these are solved in XPDRAINAGE, probably the most illuminating item. So the first item to look at is, for those who have not seen XPDRAINAGE in action before, one of my previous webinars, or missed out on one of my or other conference presentations, XPDRAINAGE with Civil 3D CAD integration is what I would call a very powerful workflow solution. So XPDRAINAGE is going to automate the design and assessment of stormwater systems and is enhanced by one-click optimizing for all runoff reduction practices. So this allows for sustainable drainage plans that we would say are quick to assemble, clear to communicate, and thoroughly reviewable. That's a very important piece, that thoroughly reviewable. So XPDRAINAGE will help you complete your projects before their deadlines, present very clear and understandable reports to constituents, and be more confident in your overall design because it's integrated so deeply into your current CAD drawing software. So we've purpose-built XPDRAINAGE to make stormwater projects more reliable and efficient. Those are very two important things for engineers. And further, to be integrated into the tools you use like Civil 3D or GIS so that everyone on your team can successfully submit quicker on every project. So we're going to, with this tool, help out beyond the water resources team. So let's have a look at the kinds of tough problems that users have solved with this product. First, I just want to show the real backbone of XPDRAINAGE and what it does. So XPDRAINAGE is very, very unique in the way that we are actually going to lay out what I'd call kind of the as-built design. So right away, we lay out against some sort of background information where the system extents will be. So hey, here's a pond, and here's actually how big it's going to be. And we're going to see in plan view all the pieces that come with that. You can see here in this video, it just takes a few seconds to lay out the items in a system. And because I have a surface, because I drew this to scale, all the input is really automatically set for me. This might not be the final elevations, might not be the final finished plan, but is really quickly kind of a 90% level detail of making sure that everything can, gravity feed or daylight out into a pond, so on and so forth. Okay, so the ability to lay things out as they'll be built, as we'll see in this next clip, we're always going to kind of lock what we're doing into the plan view. So any calculation, there's no more any spreadsheet tool to find the answer and then go figure out what that looks like in CAD or GIS. So whatever you lay out is what will be used. That's the math, right? So we solve a hydraulic problem. Well, whatever the footprint of that facility is that we're calculating, that's always shown kind of true to built in plan view. And then we're also, as you can see in this image, we're going to get the true outlet locations. We'll look at that more very briefly. and we'll get the actual lengths of pipes, so on and so forth. So there's so much detail that can come from this kind of simple concept of just actually laying something out as you go and always matching that to the calculation. So that's really the backbone of XP drainage, and really what makes it fundamentally very, very unique from really any of the other stormwater tools on the market. Certainly any other spreadsheets, that's for sure. So the first real problem that I personally spoke with a user about is something that's pretty common, and that's kind of it's the first one I bring up. So it's how to design a complex outlet structure on a pond. Okay, so that might be something that's pretty common. So I physically am in Portland, Oregon, though again I've kind of traveled all around the U.S. talking with engineers. Pretty common to have just a riser pipe sticking up in the air, right? So you might have just a single outlet, but that might have multiple orifices down the side of it, let's say, to control different rainfall events. But beyond just a complex single structure, what if you have multiple outlets? All right, so we have multiple outlets with different elevations and really different locations. Here's an image showing a pretty convoluted actually constructed outlet system. So there might be more than one of these across the perimeter of a pond. So how do we tackle that? I actually have an example we'll look at where we can see there might be a high flow channel that needs to be retrofitted. Maybe we need to add in some sort of multi-stage control structure. Everything is leaving at different points across the pond. And I guess a big one here, it's not even mentioned, is the fact that you might have many different avenues of flow getting into that pond system. So this is pretty common and pretty easily can get quite complex. So we'll look at how easy this is to lay these all out pretty intuitively in XPDRAINAGE. That's the first thing we're going to look at. The second, again, pretty simple concept, though usually with stormwater design products. Let's say we're using Excel to do some of this work. Let's say we're using some basic tool, some basic software. Usually we're focused on how big are the pipes, how big is the pond. That's usually the problems we're trying to solve, okay? How big does the system need to be? Does it fit on my site? Those are the two questions engineers need to know. XPDRAINAGE, as we kind of saw moments ago, really is going to answer that second question along with the first. So we figure out how big the system needs to be. Well, we're instantly going to see if that fits on my site. Though what happens if we need to take a step back and perform maybe more of a basic hydrology routing assessment? So the kind of classic line here is, I don't want to spend time on details, right? So I just want to have a couple minutes and figure out what do these large catchments all combine downstream into, okay? So again, pretty basic concept, though usually kind of outside the scope of what a kind of a classic stormwater design software or really a engineer might normally face. So we'll see how this is pretty easy to accommodate in XPDRAINAGE. The third problem I find really interesting. So this is how to represent a dewatering, or I might call kind of a rapid infiltration facility. So these actually kind of exist all over the place, very frequently in mining or large excavation applications. Really, most any construction phase of a project, there might need to be this kind of dewatering occur. And another example that maybe some people don't think about is airports or applications like that, where at airports we need to get water away and off the site, yet perhaps still infiltrate it, still treat it somehow. There's all sorts of chemicals around an airport, as you can imagine, sprayed on planes that are around. So we still might need to treat water, but maybe it's also just important just to get it away from the runways, okay, from the surface, and move it somewhere else. So the same idea of infiltration trenches or dewatering is going to really be important at an airport facility. So here's a pretty honest picture, I'd say, of a construction project, right? When you talk about mass grading, or when you're moving dirt around, this might be a half-constructed infiltration trench. There's that large pervious pipe, looks like maybe a 2-foot pipe maybe 3 foot that's laid down in that trench. They're going to maybe bury that with some sort of porous gravel, let's say. Maybe just leave it open like that. And ultimately, you're going to kind of pump it out and draw that water down. That's what we're talking about here. So certainly any construction phase is going to often have something like this, but in the users that I spoke with about this topic, it's actually been about mining and airport situations. So it's kind of food for thought if you run into those kind of projects. So let's see how these are dealt with in XPDRAINAGE. So let me jump over into a model. And the first one we're going to look at is the pond. So here is the site. We can see that if I turn off some of this in kind of initial layout, we'll see here is a site with this large kind of sprawling pond area, which is the kind of confluence for this kind of large semi-built up, what do we call this? Residential, rural, maybe regular urban residential zone. So this pond, in the real world, perhaps it was designed many years ago. Perhaps it was designed just based on the rational method. Maybe it's failing. One thing here that we can say is perhaps this has been observed to not be very efficient. So you can see here, even just from this aerial, how there's really a smaller pool, and then perhaps this kind of benched area. So we might find that no matter how well things were designed 30 years ago, even with the rational method, maybe they don't quite perform as well as we want them to. So maybe this pond rarely gets full, even in what's considered 100-year events. So in this case, this pond drains out to this kind of nearby slough through a channel. If you can see this channel here, one channel leaves. There's actually an outlet structure right down here in this, I'm going to say this eastern corner of our pond. So how do we represent this to start with? So we have one pond that, as we find here, is going to have different inflows into it, right? So here is one catchment that I delineated. You see that this whole area really does drain directly into the pond. One thing we can do, we can check out this catchment, this inflow area, and you'll see that the area that I've drawn is automatically updated, so on and so forth. So here's one set of inflow into this pond. Here's another inflow area. Again, I've delineated this zone. This is going to drain all into this one corner of our pond. So here I'll turn that pond back on. We can see this is going to drain into this one corner. So perhaps two different ways that water gets in. So one, water might, instead of getting in kind of a point source, well, really water is going to kind of get in all around the perimeter of this facility. So we might call that a lateral inflow. That's going to have different runoff characteristics, different resulting hydrograph than if we have a point inflow. So pretty easy to accommodate. We'll look at that in a second with the software. This is touching a bit on that larger hydrology idea. The hydrology routing we'll look at later, but we don't have to define a catchment. If you already know the values, so here is an example where I have a catchment representing this larger zone that I've kind of manually set this information. So we can manually enter in hydrographs, manually type in runoff information. And we'll see the existing site, this whole zone here is going to drain into this, ultimately this one inlet and dump out into the pond. That's what this piping water into the pond. And we'll see is I have actually drawn in the real world where the pipes daylight, where the pipes leave, or in this case, the channel leaves our pond system. Here's, of course, the outlet here. So let's take a look at the actual pond itself. So I've laid this out. As we'll see, I can look at the inlets tab. And the interesting thing to note here is I said there's a couple different ways that flow is getting in, right? So one would be, you can see this lateral inflow. Well, that would be how I would define the existing, this first area. So this area here, I'll move this out of the way a little bit. You can see this area, which really, this catchment kind of consumes the pond. Well, that's this lateral inflow. We're going to allow water to get into this facility kind of along its length, right? Different, of course, from a point source. So if you have a very long facility, let's say, or this large pond, that's a very kind of minor detail that we can overlook, but is really useful to apply, okay? And you see outlets, by default, we have kind of two freely discharging items, and that's really why this pond doesn't really fill up its residence volume. So you see I happen to have, always edit these items. We can look at the different connections. We'll see we have this channel leaving. So we have a trapezoidal channel, and we also have, so here's our trapezoidal channel with its elevations, and here's this pipe system. It might make a little more sense if I show in plan view. So we have one channel leaving. So this leaves and dumps into the slough up here. So the elevation of this reach is a bit higher than this just large 24-inch pipe. So there's really no restriction on this pipe system. And water, you can imagine, gets into this facility and drains away quite quickly, never really filling up, never quite attenuating the flow as it was expected to do. So right away, we're accommodating quite a complex series of items. So we have different flow entering our system, different ways to leave. Let's look at perhaps how we can construct these outlet systems. So the first thing I could do is I could browse to the outlet for this pipe, this piped system. Maybe we want to restrict this with maybe a more classic, maybe a riser pipe system. So you'll see here I can change this. This is our second outlet for the standard pipe. All the different outlets that you could really ever want are here. I might make this into a multiple structure. So I might have not only a high flow weir, so maybe that's like the emergency bypass. So I'll have a weir as the emergency bypass, and maybe there's a really minor low flow orifice. So we can construct this to be, there is a very kind of trickle of flow going down this pipe, and then the pond has to fill up a few feet. The pond is actually 4 feet deep. So maybe it needs to fill up a few feet before we then allow flow to spill out down that channel. And then it's almost overtopping before we engage that weir. So we can have different levels at different points. So we can have our orifice, perhaps we have something quite small, maybe just a 6-inch pipe, kind of right at the base of this system. Our weir, we could have much higher. So I could have this, maybe I'll have this be 3.5 feet high. So with a 4-foot pond, we have about top 6 inches where that weir will engage with, perhaps maybe just a 3-foot wide weir that wraps around the top of our pipe. We'll see when we have a multiple structure, we're given this depth outflow curve. Pretty clear to see what's happening here. For our channel, this trapezoidal channel, we can have a different kind of structure. Maybe I will set up just a basic weir. I can have a V-notch weir, just a broad crested weir. And I'll maybe say this is, again, just a 3-foot wide. In this case, might just be even just boards they put up, maybe some sort of metal barrier. And we can actually put this a few feet above the base. So I might put this at 7.8. So that's 2 feet off the base. So we've now built up, we have this pond, this shape, with these different controls. We'll see I actually have added some structures here in this other phase. And we can assess this system and kind of see what happens. So I'm actually running a range of rainfall events across these two phases. I'm just going to look at this one phase where I have all of the different controls that could be possibly needed around this facility added in. We can kind of see what occurs. Okay. So what we're looking at, right, when we run the software, the first thing that pops up is a stormwater control summary. Okay. And this is kind of the most important thing we tend to look at. So I can go to all storms. I'm running the 5-year and the 100-year storm. You can imagine maybe the critical storm. Well, the 100-year storm is clearly the critical. So in this case, well, percentage available, well, we're it's pretty high towards the top. Let's just see what we're dealing with here. So we have maybe further optimized this pond. We've restricted it. So now water comes in, and you see it fills up pretty far in the 5-year event. 100-year event gets right up towards the top of our freeboard. So we added in some controls just for the sake of time. You know, I won't go into further details on each control, but you get the idea that we've kind of pushed this water up kind of as high as we want to go against the freeboard, you know, based on our additional controls to this system. We can look at a comparison between different phases. So I can just go to phases, and actually I restricted both, so I could remove those restrictions and run it again. So let me jump to that design, and I'll actually take away the restrictions. I wanted to show kind of what the existing was. So let me do that right now. I'll kind of revert this facility back to being unrestricted as it was built, okay? And then you see, so I can go back to just free discharge for the different facilities, and I'll run this again, and we'll see the flow comparison between the two. Let's go back just to free discharge. And I'll run this again for that fully completed system. So let's run this one more time. I just want to show the comparison of how greatly we kind of reduced the flow by using this facility a little more intelligently. And while this is running, it's a great time to mention, go ahead. I'm not touching on a lot of the interface items, just kind of showing these problems as directly as I can. So jump to the questions field. You have something that I breeze over, you want to touch on, any questions that I move through, by all means, I'll try to answer these as we go. So ask questions, and I'll address them as we move along. Okay, so let's look at just a comparison phase report. And we can see the, in one case, the pond design. This is kind of the existing site. So for the 100-year event, we'll see, I have some graphs that I could really get into. I want to see, here is the summary. So this total, you see, I have 2 different outlet locations. So it's pretty nice. It's going to summarize these different points. So that one, this is the channel's discharge, right? So we didn't get really much flow at all out of the channel, a ton of flow out of that pipe. And you'll see the resultant flow out of the pond system is, about 10. Almost 11 CFS. And you see, if we begin to restrict flow through that pipe and really divert it into that channel, we'll see that the channel gets about 5 CFS, and we really reduce that. We really reduce the pipe system down to maybe more appropriate levels. So ultimately, we're restricting this flow down to about 6.5 CFS. Again, this is just to illustrate kind of a complex problem, and how kind of natural it is to address really complex situations. So we could spend many webinars talking about all the different ways that we can accommodate real world problems with ponds, but hopefully this shows kind of the different items that we can address with that. So let me jump to kind of the next problem we talked about. So the next one would be a trench. So here I have a site, let's say. So here is this catchment, represents this proposed building area. Okay, so this could be just a residential or just a development project that we're going to have to mass grade and really move a lot of this dirt around. That's just kind of a regular construction phase job. This could also be, we could use our imagination, this would be perhaps some sort of mining zone. So ultimately, we're going to disturb all the soil. And perhaps as a high groundwater table, perhaps just disturbing it is going to cause us some real issues. So one thing we could do, I'll just go to the inflow first. So the inflow, we could start with using a calculator. Like many things in XP drainage, you can use as many of the tools as you find useful, right? So here's a way that I could calculate the curve number. All right, here's an urban area, and in this case, newly graded, right? So newly graded, pretty poor soils, you're going to see is going to give us a 91 curve number. So here we have this pretty high curve number with, I could enter in just some basic overland characteristics. So here's the slope, roughness, and flow path, and you'll see it gives us our time of travel. So pretty useful there to do that. If you don't just know those off the top of your head, sometimes you don't, we could do a couple things here in the software. One would just be using this ruler. I find pretty useful. You could just measure. So you can see, right, predominant slope, predominant length, these different items, okay? So pretty useful to maybe see if this is my total flow path, about 1% slope, almost 1,000 feet. So using this ruler tool is pretty useful to figure out what's happening. But we define this hydrology representing this newly disturbed soil. And so all of the site drains to this extent here. So we need to apply some sort of infiltration facility. Over here on the right side, this toolbox of the software, or in this toolbox ribbon, we can see all the different stormwater control types that we can start using. Any of these you can customize, okay? So again, under this build ribbon, kind of a similar list. I like to drag and drop items into the plan view, find it pretty useful. But everything from ponds or swales, or ditches basically, to porous paving, infiltration trenches, underground tanks, rain gardens, so on and so forth. Okay, so all these different items we can use. One of these, infiltration trench, all right, I know my trench is gonna be down here, and you'll see maybe I'll add in this long, skinny trench, and I could twist that. Again, the layout's pretty useful, pretty important. So here's this trench. I actually might modify this further. Let me actually just change the shape. I'll make this actually really skinny. I only want it to be a few feet wide. In the real world, this is a very long edge of our site, but this facility might only be 4 or 5 feet wide and maybe 4 or 5 feet deep. So I'll say it's only maybe 4 feet deep. You'll see how the software automatically gives me that bottom elevation. I think it's about 30% void ratio is the fill material we're going to use. And I can manually set this to be, let's say, 5 feet wide. Okay. So one thing we could do, again, maybe you didn't quite catch it, but since I drew this facility on top of this inflow area, we automatically associate that. So the software, kind of half smart, it's going to know, well, probably draining this catchment to this facility. So it automatically gives us this inlet. So hey, this catchment area is draining, and is it a point flow or lateral flow? Oh, in this case, it's a lateral flow, right? So we can have flow enter all on the length of this facility, which is what's probably going to happen. Okay, so pretty easy to understand item there. So this inlet, we can also have, this trench. In our case, we're going to have an under drain, right? We're going to fill this area. We might have a pretty small under drain, maybe just a 6-inch pipe. Because maybe just one barrel. You can obviously make this much higher, much lower. This could be a whole webinar's worth of debate on what the Manning's value is for a pervious pipe. I'm just going to use 0.03 for this example. Okay, so a pretty rough pipe, which might be pretty appropriate. This height above base, you can imagine if we are going to, have this under drain really kind of be sitting up in the middle of our material. Well, that's what this height above base would give us. Release height is a pretty useful item when we get into more urban structures. If you want to have a retained volume, kind of a permanent storage pool in one of your filter zones. So if anyone's familiar with rain gardens, sometimes there are cases where you might want to drain an under drain at the base of your facility, though that connects into a manhole that has a little upturned elbow, okay? And so you have to actually get water above a certain height to spill out of the upturned elbow. So that's what release height gives us. So we can leave that blank. I want this to run straight out down to, in our case, a pump, and pump into this channel, okay? So pretty easy to do. So we might say that we happen to have just a a simple junction. We're just going to plop that flow right into this channel. And I can add a connection, in this case, just a standard pipe. Okay. So I'm going to drain this right in here, and let's add in our pump facility. Okay, so let's go to outlets, and you can see of these items, there's a level controlled pump where you can set some, we'd say cut in, cut out elevations. I might just say a simple pump. Okay. So I happen to have just this simple curve, which we could apply here. So you know what, this kind of wet well, so to speak, at this end needs to be 2 feet deep before the pump even starts, and you can see some basic kind of flow rates as it gets deeper. Pretty simple concept. In fact, I actually have the same thing I represented here in this kind of complete situation. And we can run, I'll turn off these other phases that we'll look at later. And I can run, and I can show you what this trench is going to do. So we just have water basically running off newly graded soil into this long trench, pumped out into this channel. You see here, again, I could look at all storms, water quality, really minor event, up to 5 and 100-year storms. Okay, we could show many more events, but just for simplicity, I show a couple. Again, critical storm, that's the 100-year event, as you can imagine. But we could get into the results for, let's say, our inflows. So we have this one catchment. I could see what that runoff would be from this area. I might change this to be the 100-year event. So here's the runoff for this system. You can also look at the actual trench itself. So let's look at the detailed results for this trench and get an idea of what's occurring here. I'll whittle this down to just inflow and outflow. You can see there's not a huge amount of attenuation or reduction in volume, I should say. We're really just getting water out, right? That's the point of these systems. Move water off the side as quick as possible. So here's the rainfall event in blue, and a little bit of a delay is water leaving this facility. We could get into all sorts of individual results series. One thing that's kind of interesting to see, for such a long facility, it might look a bit abstract, but you can see here that we could get into, all right, here is our long, skinny facility, and you see how this thing fills up over time. When I mentioned these 3D views, these are really useful to get the message across. The point of the software is to see things 18 different ways. All right, so I want to see how this is behaving in a 3D view. Okay, very, very high level. I want to see graphs showing trends. I even want to see a profile. So I could see, I'll add in a profile of this system. And we could see how this long facility behaves. Right? All this flow fills up and ultimately kind of pumps out and drains down into this channel. So it doesn't take much to add that. I know I talking in a lot of detail about this, but applying a trench like this just as a couple second exercise to define whatever area is draining into this, or just designating, you could copy and paste a hydrograph if you already have it, and then just drawing where your trench is going to be in the real world and let the software go. So pretty useful there in that regard. So I'll move over to the kind of the more watershed level assessment. So let's look at kind of the last question. If I don't want to lay out individual facilities, okay, if I don't want to lay out pipes and the elevations, even though the software can automatically find those for us. So we usually actually don't have that question be asked, because the software allows us, if we have a surface, as I showed before in that video, if you just lay out a system in the software, the elevations and lengths are automatically adopted based on real world to scale drawing and elevations on the surface. So it's really easy to get detailed just by laying something out. But if you truly want, so let's say we can pretend these are maybe a little smaller, we might have 80-acre areas. So I can draw these in the software and just define some large blocks of hydrology. So I might want to see how this all gets downstream. So we know that in the real world, this large zone is all going to drain to this corner, and there's some sort of channel, there's a bit of a ditch here. So what can we do in the software? So we don't need to get into details of pipes and outlets. We can pretty easily just add in. So I happen to have this just simple junction, I'd call it, which isn't a manhole, just kind of a calculation point. So here is this junction. I have a couple points at the downstream edges of these rainfall areas. And in fact, I can show a bit of the surface to give us an idea of kind of what we're looking at here. So you see we have this ridge running kind of across this site, and we're going to have water draining down and along the edge of this roadway, ultimately out across the road of the system. So here's our study area. You see how the water is moving down into these corners. Okay, so with that, we have a couple different options in XPDRAINAGE to move the flow. So you often see me add in, so I have connections, all these different ways to convey water. I like to right click and add connection. We could also do that up here, same thing. Usually I'm going to say, I'm going to add in some sort of pipe, some sort of channel, right? Some sort of real item. Well, we have a couple more schematic, hydrology level items we can use. So I could just say no delay, right? So hey, route that hydrograph down to the next point with no delay. Probably pretty common would be a lagged flow or an attenuated flow. So I might pick lagged flow. And I can say, all right, here is, the basic outline for that channel. And I could do that again, actually. So I could come in here and I could say, this one, I could pick attenuated. I might do lag flow again. And we'll see that I happen to be able to define that same length. So what did we just do? Okay, so we have these two connections. We'll see these through the connections form. Which looks like actually came up on my other screen. So you see here we happen to have our connections form. It's pretty simple, right? Lagged flow. I drew down the ditch, right? So 700 something feet for each of these. You see by default we have a velocity, okay? And because of length and because of the velocity we'd expect, well, here's our time of travel. I could manually change this information. I can also have this be attenuated. So there's a routing or a retention coefficient you could use if there's some sort of, maybe you're incorporating some storage within a large swale, let's say. Under lag flow, I could make this be, I don't know, let's say 4.5 minutes. We'll see that, or a lower velocity. We'll see how our time of travel is going to be expected to change. Again, I could manually type something in. That's what turns to red here when I type something in. But just based on this input, we could run the assessment and have these three areas really all meet downstream. So it takes a second to run the various rainfall events. And just with this kind of schematic concept of what's happening, by default we have these different junction points. Those summaries there. I might actually go and just look at a summary of the inflows first. So here are the different max inflow. I'll go to the 100-year event. So 4, 5, and 5 for my peak rates. Okay, and then we'll have our ultimate volumes. So here's that. I can also look at the connections. I can see how these will meet as we go downstream. Okay, so we could look at, well, critical storm, I guess we don't need to. We're looking at the 100-year event. We can see how the flow begins to stack up, moving down and ultimately out of our system. So here is the outflow from these different points along our system. Here are the inflow areas. We could ultimately compare different phases quite easily. Using this phase report, again, is we could look at the maybe existing conditions, maybe just broad brushstroke of developed conditions, okay? And we could have a very large system with these basic, cues of, it's going to take a few minutes to get down through some sort of channel, okay? Add those delays. So really quick to add in basic hydrology without getting into details of there is a pipe or there is a weir at what elevation, okay? So those really are kind of brief snapshots of the ways that we kind of answered those problems which came up from the engineering community. Any one of these we could, talk about the basic concepts and some of the, best practices behind hydrology routing, behind pond and, pond meets open channel or pond meets a pipe system. But hopefully just the kind of kernel of what we can do with the software and really how easy it was to approach with XPDRAINAGE was really the point of the webinar today. So that's what I was hoping to show. Catherine, I think, has some questions she'd like to ask, and I'm going to look through the questions here and kind of see what's come in and talk to those. So anything, questions you have, go ahead and type them in, and I'll get to those here shortly. So Catherine?
All right, thanks, Zach. So Zach presented a lot of good information today, and at the end of our webinars, we always like to give everyone an opportunity to request some more information. So I'm just going to launch a poll real quick, and we won't share the results of these, but we'd like to know if you would like some pricing information for XPDRAINAGE. Do you want to see if Zach could schedule some time with you to expand further on the functions of XPDRAINAGE that you saw in today's presentation? Or do you have any other specific questions or comments, or just nothing at this time? And I will give everyone just a couple more seconds to vote. All right, so it looks like we have a good amount of people who voted. So I'm just going to close that poll. All right, so now for some information that I'm sure quite a few of you are waiting for, PDH certificate information. So remember that in order to receive your PDH certificate, you must have registered before or during this webinar. So if you are registered later today, you'll receive an email from ameducation@xpsolutions.com. But because this is a general email address, sometimes they get stuck in spam or junk folders. So just make sure you check there if you don't see an email by this address by the end of the day. And when you receive the email, there will be a link. Click on the link and it'll take you to a survey where you'll have an option to provide feedback about today's webinar. You can offer any suggestions for future webinars or request more information. But if you don't want to participate in the survey, you don't have to. You can click right through it. But we would always love your feedback. We read through all your comments and we use this information to help improve our future webinars. So once you completed the survey or you click through it, you'll be taken to a place where you can type your name as you'd want to have it appear on your certificate. But there is a password. So the password for today's webinar is outlet. So please write this down because you will need it later to access your certificate. Again, the password is outlet. And if for some reason you have an issue where you can't access this section, don't worry, we do have a backup plan. So after you click through the survey, you'll receive a confirmation email, and this email will include the link that'll take you directly to the place where you input your name and password, again, which is outlet. And then certificates will be available for just several days. And so if you watch this as a group, everyone still needs to have registered previously to receive a certificate, but only one person will show as having logged in. So right after the webinar, please send us a list of all registered attendees to ameducation@xpsolutions.com. And we'll be sending those out after today's last presentation. So the sooner you can send those lists, the better. Zach, are there any questions that you'd like to answer to the group?
Yeah, thanks, Catherine. There sure is a couple questions here. So the first one is, let's see here. So I'll just read it off. So if we put infiltration, or if we use an infiltration trench that isn't necessarily gravity fed, then what happens? So a couple things we could do. I'll actually go into the software and we could look at this. So let me jump back to a different phase. So again, I designated kind of a simple pump idea here. So again, whatever your site, there's a million different ways this could be configured, but does water get into X facility? So that's just the basic inflow area, drains in one way or another to this trench. If it doesn't drain in and there's some sort of pumped system, if there's some collection, right? The point of XPDRAINAGE is we can define these different elements. We can define, simple pumps. We can define, channels, whatnot. So really just define as much of the system as you want to, and go from there. So in this case, I'm saying water ultimately is going to get into this trench. Okay, is there another pump in the middle of the field? I could represent that. Maybe if I am just making a broader assumption and I just want to see how a trench behaves, maybe I only do this. Maybe I define maybe a couple of the maybe pumped or just gravity trenches that feed into this other trench, right? So we can represent this however we want to. In this case, this facility was kind of pushed out into this channel, right, after a certain depth. So this trench wasn't necessarily, gravity feeding into this channel. So that can be represented a number of ways. Basically, like anything here in XPDRAINAGE, you can take it into as much detail as you want, okay? Looks like another question that came in actually isn't about XPDRAINAGE. Looks like there's someone asking about XPSWIM. And the idea is, can you create lateral inflows like I had shown in the other example, or even in this case, I use that lateral inflow idea. Can you do the same thing in XPSWIM? And no. So you can't apply the same type of lateral inflow in XPSWIM as you can in XPDRAINAGE. Now, this really isn't a webinar talking about XPSWIM, but certainly if there are questions about that and how you configure things in XPSWIM, there's a number of people here that we'd be happy to talk to you about that. Obviously, swim is a little different. The fact that it doesn't represent the real world outlines, of these facilities the way that XPDRAINAGE does. So that's kind of why drainage is, kind of purpose built for this design world, where we need to actually see the layouts and if they're going to fit on the site, so on and so forth. Okay. So I think those are the two questions that weren't already answered. So I'd say if there's anyone who is interested, again, my name is Zach Sample. I am be happy to talk with anyone with further questions that they might have. There's a whole team of technical people, as you can imagine here at Innovise, that can go through any of your individual situations and talk to some, kind of your hard problems. That's what we do. That's kind of the fun part of talking with engineers. So again, any questions, let us know, and thank you very much for joining. It was my pleasure.